we continue with the third with the 10th unit, and we'll start with the third lecture for the 10th unit, the third part for the 10th unit. Remember, in the 10th unit we were looking at universal schemes, and today we'll start with this called Arithmetic Code, which is a very useful code. It's a practical scheme. A goal motivated by universal compression is to take this distribution Qn of x, Qn of xn. This distribution is a, so let's say it's a PMF, probability mass function, over sequences of length n from the alphabet x. That's what this distribution is. And we would take this distribution and we would like to come up with codes. We like to come up with a code. So we want just one second. A prefix-free code with code word lengths log 1 by Qnx. Okay, that's what we want. Now, we have already seen one such code, namely the Huffman code. In fact, Huffman code is better than this one. So we want lengths less than equal to this, but we have seen Shannon code which does this. But all those code require you to work with the entire sequence xn. And for large n, this finding probabilities for entire sequence xn, that's formidable because there are a lot of there are many sequences, and this probability is on the entire sequence. So those schemes are not feasible here in this context. So what we want specifically is we want a scheme that uses probability associated with symbol I. So let's say Qn, this is the probability of symbol I given all the past guys, to encode symbol xi. So it encodes symbol xi after it has already encoded x1 to xi minus 1 in the previous slots. So this kind of scheme is sort of a streaming implementation, and it doesn't require you to know the sequence in advance. Can operate symbol by symbol. So at time I, it sees symbol I, and then it uses only the information required to encode symbol I. Obviously, it knows the context, the past. This is when I'm putting it this way, it is almost practical. Further, when you go in practice, it is difficult to remember the entire past as well. So you most likely will make don't want to remember this entire past sequence, and something very little about it is required. And in fact, that is true. All you need the past for here is to compute this probability, and later we'll see that this probability, the Qn that we will use, that we'll talk about in the next lecture. This lecture we assume this Qn. Actually, it doesn't require you to remember all the symbols. It requires you to remember very little about these symbols. But for now, we assume that all this is given, and so you can compute this probability of this current symbol and encode it. Okay. And also, then this is at the encoder side. Then at the decoder side, use a different color. At the decoder side, again you go sequentially. Upon decoding, so you have already decoded the past, and let me put a hat to indicate that they are decoded values. But of course, we are looking for error-free scheme, so this is equal to xj hat is exactly equal to xj. So after you have decoded this past, guys, you can decode x hat I using, so now you again need to know the model, and the model is just q of qn of xi given xi minus 1. Okay, so that's schemes where you can go one by one, and if you notice what's happening here, the first symbol which enters gets encoded first and then also gets decoded first. So such schemes are called FIFO schemes, first in, first out. Okay. Perhaps you have heard the word FIFO in different contexts of queues. The same phrase is used here. So it's the first symbol to be encoded, first symbol to be that you get. X1 was the first one that you see. First in, first out. That's what a FIFO scheme is. So this first in, first out schemes, that's what you want out of this scheme. Okay, let me try to draw a block diagram to explain how this. Let me try to draw a block diagram to show how this scheme actually works. So let's see. So you have an encoder, and you have a decoder, and then there's a third entity, which is the model. So this is the operation at time t. This is the operation at t. Okay. So the encoder sees the sequence of symbols x1. I'll write it in a specific order. So the symbols are x1, x2, x3, so on and so forth, xt, and then the future symbols which it has not seen yet. So at the time when xt is in, that's the time t, it has already, these symbols are already sent. So at this time the encoder sees this symbol. Now to encode this symbol, encoder needs more. The encoder needs some access from the model. So it needs the probability of this incoming symbol, qn of xt, and this can depend on probability of the past symbols. Yeah. So in that sense, the model also knows this past and gives. So all this part of providing this current probability is taken care of by the model. There's some. So this think of it as a code. This is one part of the code. This is the other part of the code, which code as in the program that you have written, the model that gives it. And then this is the output bits. Output compressed bits. And the decoder now applies the decoding algorithm to the same bit. So now decoder again, the decoder on its side does the same thing. It's decoding those guys one at a time. So it has already decoded xt hat, but before that it has already decoded all the previous guys. Okay. And once again, it has already decoded these guys. So these guys can access the model and ask the decoder can use them to get qn for the next guy. So it knows the distribution that we are using for the next guy once it has decoded all these guys. Yeah, sorry about this. There is some problem with my software. Anyway, so just to distinguish these guys, I've lost all my colors, but I won't write it again. I'll just continue from here. So yeah, so this model, this part was accessed by the encoder, and the other part here is accessed by the decoder. Okay, not accessed by the same way. So because the decoder doesn't know what the previous symbols are. So when the decoder accesses the model, it must ask the model what is the next probability distribution you're using for the current symbol, given that I have decoded these guys in the past. Okay, it must use this decoded values when it's accessing this model. It cannot use this original values because it doesn't know. So as they come, it accesses this model, and now he gets the model again, which he can use to decode the next symbol. Okay, so these are the kind of schemes we are looking for. This FIFO schemes, and one such scheme is the so-called arithmetic code. That's the scheme we will look at now. Okay, so this arithmetic code is it's an interval representation of a prefix-free code. So remember, we had seen that we can represent prefix-free codes either using graphs or using intervals, and Huffman code uses graphs generally. And now this interval representation will be used in this arithmetic code. What happens in this scheme? We will follow this template here, that you are given this distribution, and you want to encode the next symbol. So what we do is, at each time t, let me just write it as an algorithm in a rough way. So I'll provide typed formal notes, but let me explain it roughly. So you always maintain an interval representing your code here in this scheme, in this algorithm. Throughout you maintain an interval. So maintain an interval I in 0, 1. This scheme does. So in the beginning, this interval is set to the whole interval 0, 1. Okay, that's the starting point. So we'll call this the initial step. I equal to 0, 1. Now what do we do as we see symbols? At time t, so what you can do at time t, we would like to update this interval. Maybe I should call this I0, and at time t we'll find this interval it. Okay, so what we take is, the rough idea is divide it into sub intervals with so this is some interval that you have here. You are maintaining this interval it minus 1. So divide it minus 1 into sub intervals like this, and the lengths of these sub intervals, this length, first part, second part, these lengths are kept proportional to, length as a fraction of the original interval's length, are kept proportional to probabilities of symbols. So these sub intervals correspond to different symbols with length of sub intervals, maybe so divide it, maybe I'll be more specific, it minus 1 into sub intervals. So I'll label these sub intervals. These sub intervals are one corresponding to each symbol. So these sub intervals are it minus 1 comma x for different x in your alphabet. Okay, these are your different sub intervals, such that the length of this subinterval it minus 1 x divided by the length of the original interval it minus 1. This is length. I'll write it on the side. This is defined as the length of interval I. Right. So this, what we want is that this length is exactly equal to Qn of your Th symbol being equal to x, given that the past symbols are whatever you have seen till the past point. Okay, these are your different subintervals. I think I formally define it, so I can just call it A. So this is the first thing you do. So you access the model and you find out this partition. And then the part you choose, let it, the next interval is it minus 1 of xt. Okay. So you choose the subinterval corresponding to the symbol that you have seen. Okay. That's the one you retain for the next one. And you keep on going this way. Okay. So you stop at time n. Okay. When you stop, you have an interval in of length. So what's the length of in? That's an important calculation. Mod in. So in, you can write it as the first interval times the second interval by first interval, so on and so forth, and the nth interval by in minus 1 interval. You can always write it this way. But if you decompose the length of in this way, what can you say about each of this part? The first part is the probability of the first symbol under Q. That's Qn of x1. Second part by our algorithm is Qn of x2 given x1. And the last part is Qn of xn given the past. Okay, so this is what you get. But this is exactly equal to Qn of x1 to xn. Okay, so the length of the interval is proportional to the probability. It's exactly equal to the probability. That's what you wanted. You want not, so, but we have not decided. We have not told you what the code word is. We have not decided what the code word is. All we have observed is that when the algorithm is applied for n steps, it's run on n symbols. The length of the interval is exactly equal to the probability that you want to associate with that sequence. So now what we have done is we have identified this interval Qn that corresponds to a sequence that we want to encode. But what still remains is to find binary sequences to represent these intervals. And a problem there is that we need to ensure that the final binary sequences corresponding to different intervals constitute a prefix-free code. So the question is, how do we represent these final intervals using a prefix-free code? Okay. And we do that using a sort of a classic scheme. We do that using the so-called Shannon-Fano-Elias code, which is a way for representing this disjoint intervals to form a prefix-free code. And the scheme is very simple. What we do is the following: we represent the interval I. So this interval will start somewhere and end somewhere. I using the L So we compute this L. L is log of b minus a. Remember, this b minus a is the probability of the sequence. So this is sort of minus log p part plus 1. Okay, minus log p part plus 1. We represent it using the L most significant bits in the binary representation of the midpoint of the interval a plus b by 2. So there are two parts to the scheme. First is that we use this midpoint, we compute this midpoint, and then represent it using these many bits. Okay, that's the scheme. Okay, so what do we get out of this scheme? We have to claim that the resulting code is actually prefix free. So to see that the resulting code is prefix free, we try to figure out where each part of this code lies. Okay, that's how we will show that the resulting code is prefix free. So that is, we look at the different code words corresponding to different intervals and show that any prefix of this code word, first we show that the numbers corresponding to those code words cannot be outside the interval. Then we show that any prefix of that code word, the numbers corresponding to those, can also not be outside those intervals, whereby the codes must be prefix free. So let me describe this proof. So this code is prefix free. That's the claim which we have to prove. So how do we prove this thing? So look at this interval I. Remember, different sequences will correspond to different code words or different intervals. And we have taken its midpoint, a plus b by 2. And we have taken the L most significant bits of this a plus b by 2. Where do those, so this number AL, let's say, let C equal to 0. So how do we do this? So suppose a plus b by 2 is this binary number 0.r1 r2 blah blah blah, can go on for can go on continuously without terminating. Let C be this L most significant bits that we choose. So C is this number which corresponds to this L most significant bits. Where can C lie in relation to a plus b by 2? Note that C takes the first L bit, so C must be on this side of a plus b by 2. But it cannot go all the way to A. It must stop at some point here. And this difference must be less than or equal to 2 to the power minus L. So since L equals to minus log b minus a plus 1, 2 to the power minus L is less than or equal to b minus a by 2. Therefore, this code word C can only lie in this part. So this is where C can lie. Okay. Now suppose that y1 to ym has r1 to rl as its prefix. Okay, so you have the sequence y1 to yn, it has r1 to rl its prefix. Consider the number a prime equals to 0.y1 to ym. Where can this a prime lie? We know that this a prime and C have the first L bits same. And in fact, C can only be on the left of A prime. So C is somewhere here. A prime is to the right of C. So A prime can be anywhere here. But also A prime can at most be 2 to the power minus L away from this, because the first L bits coincide. So A prime can at most be 2 to the power minus L away from this. So it can only be this one. So A prime must lie here. What we have used here is A prime. C can only be smaller than A prime because this is the first L bit here. And A prime can at most be this plus 2 to the power minus L. So which can at most, so C can be somewhere here, so A prime can only be here. So the conclusion from this observation is that both C and A prime must lie in I. And therefore, if there is another interval, then the code word C corresponding to that interval is a prefix of this code word C corresponding to our interval I, then there is a contradiction, because it must lie, that new C prime, the code word of some other interval, must lie within I by this second property. But by the first property, that code word must lie in its corresponding interval, and these two intervals are disjoint. So therefore, this code must be prefix free. Okay. All right. So great. This is very easy. What's the average length of this code? So this B minus A is the probability of this sequence EX minus log ceil of that plus 1. So you can check the average length of the resulting code is expected value of minus log px ceil of that. So ceil of that is at most this plus 1 and plus another 1 because we're adding. So this is less than equal to hp plus 2. So we don't worry about this extra 1 that we got, but it's still roughly hp. We may pay 2 extra bit overall for the n length sequence. Okay. So no problem. Okay, so this is a scheme described abstractly. You start with some interval. At each step, you divide the interval in proportion to the probabilities of the incoming symbol, and then you find the next interval. You keep on doing, and you keep on going this way, and you stop once you've seen all the symbol. Finally, you represent the resulting interval in this manner using the Shannon-Fano-Elias code. And when we show it's prefix free and the average length is at most hp plus 2. Before we proceed to see how to decode, let's take an example. So suppose Qn. So let's take alphabet X equals to A B C D, and let's take n, the length of the sequence, to be 4, and let's take Qn of these 4 symbols x1, x2, x3, x4, just a product distribution, is equal to product I equal to 1 to 4 p of xi, where p of a, so we'll just take any simple probability distribution. So let's say P of A is, let me put out an example from the note so that I'm consistent. Where P of A is 1 by 8, P of B is half, and P of C is 1 by 4. P of D is again 1 by 8. It's some example I'm taking. Okay. So let's see how the previous algorithm will encode this guy. So I'll go step by step. In the first step, you have this interval 0 to 1. I'll just draw it this way. And you divide it into this 4 parts. So this first part is 0.001, then 0.010012 to half of the interval. So that's 0.101, and then plus 1/4. So yeah, 1/8. So another 1/8 can be added. So don't proportions may be all wrong here. Let me try my best to at least half, 1/4, 1/8, right? So this is 0.001. That's 1/8, and then you add another half to it. So 1/4, another 1/4, another 1/4, another 1/4. So that's half roughly 0.101, and then you add another 1/4 to it. Um, So this is another 1/4 to it, so 0.111, and then you add 1/8. You get this. So these are my 4 intervals corresponding to A, B, C, and D. Okay, so first symbol is A. So I1 is equal to 0 to 0.001. That's my first interval. Now, in the next step, okay, so we want to, I didn't describe which sequence to encode. Encode the sequence A, B, maybe A, C, B, B. Okay, A, C, B, B. This is the sequence we're trying to encode. So first symbol is A. So the first interval that we get is this one. Now, so now we are inside this interval I1. We'll zoom it in. 0, and the right side is now 0.001, and we'll do the same partition now. So 0 plus 0.001 of this length. Okay, so what is this first? 0.001, 001. Okay, and you keep on going same way. So 0.001 of this length. So you will get this. So what is the second symbol now? Now second symbol is, this is in the same proportion from here, by the way. Same proportion, same proportion. So what is this number if it's in the same proportion? This is 0.001 minus the 1/4 of it, 1/8 of it. So this second number is, I think this interval here corresponds to 0.00101 to 0.000111. Okay, so 3 zeros and then 10111. Okay, so this is the second interval. So now I2 becomes this guy. Please check these calculations. I'm just bringing it out from my notes. Maybe some small mistake. Okay, and you keep on repeating this. So next step, you get I3 now corresponding to symbol B, and so this I3 looks like 0.00010101 and 0.00011. 1 0 1 1 1. And the fourth step you have I4. This guy now looks like 0.00. You can pause the video and try to do this calculation and check if this calculations that I'm writing here are correct. 0.000 10101. Yeah. Just a basic check here. 1010111. Okay, so that's at least what I have calculated. Okay, so this is our final interval I4 just by repeating that procedure. Now how do we represent this guy? We take the mean. So this is my A, this is B. What is the mean of A plus B? Mean of A and B. The mean of A, B, the midpoint of this interval is A plus B by 2, which is equal to 0.01010 101 and 110. So this mean becomes so what are these 101 here and this is 110. So it becomes 110. Okay, that's the mean. Right. And so what is the length of this interval? The length of I4 B minus A equals to 2 to the power minus 9. You can check this. So this implies so they just differ in this bit, which is 1 2 3 4 5 6 7 8 9. 2 to the power minus 9, which implies that the length that we choose is 11. So these are 1 2 3 4 5 6 7 8 9 10 11. So implies the code word corresponding to this interval is, so there are 10 bits here, but we need 11, so we add another 0 0 0 0 1 0 1 0 1 1 0, and this is the extra 0 that we add to make it 11 bits. Okay, so this is our code word. Now so that was we can compute this thing. One thing you may have noticed about this algorithm is that it looks practical, but we have to compute this very high resolution numbers, and that's what makes it less practical. As the length of the sequence increases, this resolution increases quite a bit, and at some point your computer will not be able to handle it. In fact, very quickly your computer will not be able to handle it. So one thing that people do when they come up with practical algorithm is try to ensure that this resolution doesn't blow up. And in fact, there's a lot of theory for even those kind of algorithms, but we are not looking at those algorithms. There you may not be able to get this HP plus 2. You may have some additional loss, but it will be more practical in the sense that you don't need infinite precision to make these computations. All this was fine, but we already reached a resolution of about 10-11 bits, right? So if you continue just with 4 symbols, so if you continue this computation, you will reach a very high resolution, and with such simple probabilities. Okay, so with this example, I hope the encoding procedure here is a little bit clear. Now let's look at the decoding procedure. So in decoder, what you do is you just invert the step that you have above. The same steps that we just saw, you just invert it. So rather than describing the algorithmic procedure, which is written in the notes that I am providing, I'll just walk you through this example. Decoder just invert the encoding procedure. Note that the decoder already has access to that model, but it doesn't know the symbol, so it cannot right away access the model. So we will go with this example itself. We illustrate using the example above. Okay, so let's see. So we are given as input this sequence, given this code word 0 0 0 1 0 1 0 1 1 0 0. And we'll think of the binary number corresponding to this sequence and see where that binary number lies. So in the first step, we start with our model. We look at this partition. Okay, this a model already tells us this partition, and we put that number 0 0 1. So let me just take this partition here. Okay, so this is the partition given to us in the first step. This the model gives us. We will take this number, this guy here, and see where it lies. It starts with this 0 0. It starts with 3 zeros, so it must lie in this part. Okay, so this number lies somewhere here. So this implies that the first symbol must be A. So x1 equals to A because this interval was lying, because this number that we are given lies in this interval. So the first symbol must be A. Okay, so the first symbol is A. But that also tells us what interval to take in the next step. What partition to take in the next step. And so the next step we see, this is the new interval. Let me take this now. This is from the encoder. So once I have A, I can ask model for the next steps interval. Note that I never am accessing the model to find out the interval for the entire thing. One second. Take this guy here. Copy it. Let me put it here. Get the decoder. So now we access the model and we ask the model to tell us the next interval. And so model gives this guy, because I already know this first symbol is x1. But I know the entire number, it's 0.00101. So let's see where that guy lies. So 3 zeros and 101, so it's more than 101, but less than 111. So it lies somewhere here. So this is the next point where it lies. Okay. So this corresponds to C, so implies that the next symbol x2 is C. And now you will continue this way. You will zoom this interval and see where the number lies and keep on doing it. And you will see that you will recover the sequence x3 is B and x4 is again B. Okay, that's how this protocol works. So one important thing to notice here, I insist on this. I insist that you look at it carefully. I'm never accessing model directly for the entire sequence. I'm accessing model one by one, only asking for the probability distribution of the next symbol. And this is very important in practice. I never ask for distribution for a large sequence. Only for this each symbol, I go symbol by symbol and get the distribution for the next symbol. Okay, so that's the description of the algorithm. In my notes, I've given the formal description, but it is better to work out an example to understand this. So in conclusion, we have a sort of practical, put it in quotes, practical algorithm that attains average length of that attains average length not exceeding h of qn plus 2 and requires the model to provide qn of xt, so the distribution for the next symbol qn given all the past times at time t. Okay. So this scheme is there, and now what we will do in the next lecture is see that if you can somehow come up with a probability assignment like this, then how so we can already attain this. Now only thing that remains is how to come up with this probability assignment at each time so that Rn star is attained. So we want the optimal probability assignment which attains Rn star. If Qn attains Rn star, we get a scheme with regret less than Rn star plus 2. Okay, and remember this Rn star is very small. We already saw a proof that this is less than some log n plus 1, or for binary case log n plus 1 at least, and in general cardinality of k minus 1 log n plus 1, and so we have roughly a log n scheme which will come. So the only thing which we need to do now, the only question which remains is how to assign Qn that attains Rn star, the best probability assignment. And that's what we'll see in the next class. See you in the next lecture.